Hello guys, today we will discuss electric field lines and its properties. The concept of electric field lines was first introduced by Michael Faraday. It is an aid or way to visualizing electric fields around charged configuration. Faraday called them lines of force, but this term is something misleading, especially in case of magnetic fields. The more appropriate term is field lines. We say electric field lines. So an electric field line is an imaginary line. It is an imaginary line. In general, it is a curve drawn in such a way that if we draw a tangent at any point to it, then this tangent shows the direction of electric field at that point. Suppose this is a point A and the electric field, this is suppose E1 is the electric field at the point A. Then we take suppose another point here B, then draw another tangent, then that gives the direction of electric field E2 at that point. So an electric field in general a curve drawn in such a way that tangent to it at any point shows the direction of electric field at that point. If we place a positive charge, test charge at a point, then that tangent gives the direction of force on that charge, or it also gives the direction of acceleration at that point. So let us draw some field lines of some charge configuration. Here we take an isolated positive charge and the field lines are radially outward, and in case of negatively isolated charge the field lines are radially inward. Then we take two positive charges. This is plus Q and this is also plus Q, and here these are the field patterns, and in case of two equal and opposite charges these are the field lines. So let us discuss some properties. Properties of field lines. Field lines start from positive charges and end at negative charges. Like this. This is a positive charge. Field line starts from this. From an isolated positive charge, the field lines are radially outward. If there is a single charge, then the field lines ends at infinity. These field lines ends at infinity. And in case of negative charge, single negative charge, the field lines they starts from infinity. This is from infinity. So first property, field lines start from positive charges and end at negative charges. If there is a single charge, they start or end at infinity. Then second property, electric field lines can be taken to be continuous, not breaking, without any break. Electric field lines can be taken to be continuous curve without any break. Then third property, two field lines, very important property, two field lines never cross each other. Never cross each other. Suppose we take two field line, this is one field line and this is another field line. Suppose they cross at a point, at this point. Then we draw, there are two possible tangents. This is one tangent and this is another tangent. So this tangent gives electric field, suppose this is E1, and this tangent gives another electric field E2. So two possible electric fields exist at a single point, which is impossible. There is only unique electric field and it has unique direction. So two lines of force never cross. Electric field lines do not form any closed loop. Closed loop means this is your closed loop, but electric field lines do not form any closed loop. So if we consider two charges, suppose this is your positive and this is negative, so this is one field line, this is other field line, but they do not form a closed loop because the field line does not pass inside the conductor. So electric field lines do not form any closed loop. Field lines meet the surface of conductor at right angles. Suppose we consider a conductor, this is a conductor, and here field lines are perpendicular to the surface of the conductor like this. This is right angle, 90 degree. These are the field lines which are normal to the surface of the conductor. Inside the conductor, electric field is 0 because charge always reside on its surface. Next property, field lines tend to contract lengthwise. This is on account of unlike charges. In case of attraction of two charges, that is, suppose this is your positive charge and this is your negative charge, this is the field line, this is other field line, this is other field line. So these field lines tend to contract lengthwise. And in case of two like charges, they tend to exert pressure, lateral pressure, like this. These two lines exerts pressure. And exert lateral pressure. This is in case of like charges. Next property, the density of field lines. The density of field lines. Density of field lines means number of lines per transverse area. The density of field lines is proportional to the magnitude of the electric field. The field may be strong or weak. The field is strong where the lines are close together, and weak where the lines are far apart. In this case, these lines near the charge, they are close together. So this is the region of stronger field. The field near the charge, stronger field. But further, the field lines are they are wider, they are separated. So at the further end, electric field is weaker. So closeness of lines means stronger the field. Let us discuss uniform field. An uniform field has constant strength and direction at every point in the region of space. They are represented by parallel equispaced lines. The distance between two lines are equal and these lines are parallel. So this represents uniform electric field. Consider two plates. One is positively charged and other is negatively charged. So lines of starts from positive plate and ends on negative plates. So these are the field lines, and the field created by these two plates, positive plate and negative plates, is uniform. This is your uniform field, and this is the case of, that is, parallel plate capacitor. But field due to isolated charge is non-uniform. So the field lines are not parallel. Here the field lines are not parallel. So this field is non-uniform. Non-uniform field means the strength of the field varies and the field lines are not parallel. In this case, field nearer the charge is stronger and farther from the charge is weaker. So this is the non-uniform field. We can represent the field, non-uniform field, like this, non-parallel. In this case, this is the non-uniform field. This is the region of strong field, where the density of field lines is more here, and this region is the weaker field, where the field lines are separated out. Field due to positively charged sheet are uniform. Similarly, fields due to negatively charged sheets are also uniform. Here the field is inward. The arrows are pointing inward. Let us discuss some examples. A metal sphere is placed in a uniform electric field whose path is followed by lines of force. This is a metal sphere and it is a conductor. So in a conductor, the lines of force meet on its surface normally, So this is the case 4. Here the lines of force meets on the surface normally, and inside the conductor electric field is 0. So case 2 and 3 are not valid here, because here lines of force passes through the sphere, so these two are not valid. Then 1 and 4. In case of 1, here the lines of force meets obliquely at the surface, but in case of 4 it meets on the surface normally. So the answer is your path 4. Next example, these are the field lines. There are two charges, one is A, another is B. Charge of A is QA, charge of B is QB. Question is the field is uniform? Answer is no, because here the field lines are not parallel. What are signs of QA and QB? We know that lines of force starts from positive charge and ends on negative charge. So QA is positive and QB is negative. Then determine the ratio of QA and QB. So charge QA and QB are related to number of lines of force. The number of lines of force emerging from QA is 12. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 lines are emerging from QA and 6 lines meet at B. So ratio is QA by QB, that is 12 by 6, that is equal to 2. Next example. So there are 3 field lines. So question is, what is the direction of electrostatic force on a positive test charge placed at A and at B? At which point A or B will the acceleration of the test charge be greater if the charge is released? So these 3 lines are closer on left side and they are separated on right side. So at A field is stronger and at B field is weak. And we know that direction of electric field or electric force can be determined by drawing the tangent. So tangent at A and B gives the direction. Tangent at A and B gives the direction. And acceleration at A is greater than acceleration at B, because electric field strength at A is greater than electric field strength at B. EA is greater than EB. Thank you.